Are you all good with whatever we have done in the previous lecture? Okay. Okay, thank you. Are you all good with whatever we have done in the previous lecture? Do you have any questions? No questions? Okay. So I want to remind you that next Monday, today the homework 00 is due on today, right? Homework 1 is due next Monday. Next Monday is a Labor Day. Even though it's a Labor Day, the homework is still due on Monday. Okay, number 1. Number 2, so you can finish it before Sunday so that you can be free on Labor Day. Okay. The second thing is the quiz is going to be on Wednesday next week, quiz 1. It's going to be dealing with variable separable, method of integrating factor, some applications that we're going to do today. I'm going to post the details of it on Canvas sometime during this week, and I will email you all as well. So please keep looking for that information. Okay. Now, okay, where were we in the last lecture? The last week we were wanting to solve the first order differential equations, right? And we said there are 5 different ways. One is the graphical method. The second one is the variable separable method. The third one is the method of integrating factors. The fourth method is Laplace transforms. The fifth one is numerical methods. Okay, so we began our discussion with the graphical method. We discussed how, without really solving it, we were able to sketch the graphs of the solutions approximately. Okay. The next one is the variable separable method. The ones we did turned out to be nonlinear problems. We were able to, fortunately for us, we were able to bring the terms with y on one side, the t on the other side. We integrated both sides and we were able to obtain the solution. When we obtained the solution for the first order differential equations using variable separable, sometimes we got explicit solutions, sometimes we got implicit solutions. Okay, remember that. And then we studied method of integrating factors. When we studied method of integrating factors, the first thing that we wanted to do was, when we studied the method of integrating factor, I told you at that time to find a solution, you should either run through the proof or you should memorize the formula. Both seemed a little difficult. So we found a happy medium and we found a process to go after that. So the process was, the first step is to make the coefficient of y prime equals 1. Then identify what is p of t, identify what is q of t. Then find the find the integrating factor, which is nothing but the exponential of integral of p of t. And then once you get that, you will be able to write it like derivative of the integrating factor times the dependent variable on the left side is equal to the integrating factor times the right hand side of the function q. And after that, you integrated both sides and obtained the solution, right? And when you obtain the solution, what you always ended up getting, we did only 2 problems of those kinds, and whenever we did, in those 2 problems, we got an explicit solution. So whenever we use method of integrating factor, we got the explicit solution. Whenever we use the method of variable separable, I was not able to generalize. Sometimes we got explicit, sometimes we got implicit. So it depends on the problem. Is that clear? That's all we have done so far. Are we good so far? So what is the plan for the day? The plan is that we're going to continue the discussion a little bit more on method of integrating factor, a tiny bit more, and then move on to applications. Okay, that's what we're going to do today. The next lecture is going to be more theoretical in nature, more mathematical in nature. Hopefully you will find it interesting. this week. I mean, hopefully you will find this week interesting, because the next week is from next week on, it's going to be highly computational. That means, okay, here is the reason, here is the justification, here is the process, compute. That's how it's going to be. But this week, the next Thursday is going to be a little conceptual in nature. So let's hope that we all get through this week without any hiccups. Okay. So we did this problem and we got this y is the explicit solution and all that. So I want to go back a little more. The problem was y prime plus y over t is going to be, I think it is y over t is going to be cosine t, if I'm right. And the solution turned out to be y equals c over t plus cosine t over t plus sine t over t plus sine t, where my value of t is bigger than 0. I wanted t bigger than, if t is equal to 0, there is no differential equation or the solution becomes unbounded. So we want the t to be not equal to 0. So the t cannot be equal to 0 means t can be either positive or negative. And in this scenario, just there is no rationale. I just chose t to be positive. Okay, that's purely nothing. I mean, I just specified it like this. So in this, what is this? I mean, remember there are two kinds of terms, the first term and the second and third terms together. What is so? In the first term, there is an arbitrary constant. Okay, there is an arbitrary constant c, and in the second and third term, there is no arbitrary constant. Okay, that's the difference, right? So this is the first order differential equation. So when you carried out method of integrating factor, you get one arbitrary constant, which is c. So how many possibilities are there for you to choose the c? There are infinitely many possibilities, so you get infinitely many solutions. So c is called a parameter or one parameter family of solution. We spoke about it, right? So now so your solution y can be treated as a sum of two kinds of functions. One is yc and the other is yp. Yc is the one with the arbitrary constant c. Yp is the one with no arbitrary constant. Yp is that part of the solution with no arbitrary constant. So yc is called a complementary solution. Complementary solution. This is a solution of the homogeneous differential equation. Homogeneous means right hand side is equal to 0. Homogeneous differential equation. So that means in this case it is a differential. It is a solution of y prime plus y of t equals 0. Okay, so yc is not the solution of, remember that yc is not the solution of the differential equation y prime plus y of t equals cosine t. That means when the right side is not 0, then yc is not the solution. If the right side is 0, then it is the solution. Is that clear? Then similarly, you can extend this concept to, okay, yp is the particular solution. Okay, particular solution is the solution of is the solution of a non-homogeneous differential equation. In other words, the right hand side is not equal to 0. Okay, so that means in this case yp is the solution of, let me add it here, yp is the solution of y prime plus y over t equals cosine of t.
Can you go back for a second?
Okay, so yp is not the solution of the homogeneous differential equation. Remember that yp is not the solution of y prime plus y of t equals 0. But somehow you can see that the sum yc plus yp is the solution of the problem y prime plus y of t equals cosine t. Now, why is it happening? Because it is just by the construction. I'm not going to go over the proof again, all over again. We very briefly did the proof. And you see, when I said q equals 0, q is the right hand side. When I said q equals 0, I got an exponential term where with k is an arbitrary constant. So whenever I get an arbitrary constant, that's the solution of the homogeneous differential equation. Whenever I don't have, then I imitated the solution in such a way that whenever I got a term without the arbitrary constant, that's a particular solution that satisfies a non-homogeneous differential equation. It's pretty much by the proof, but I demonstrated it very quickly so that you have an idea of what is going on, and from there we can make these conclusions. Clear? Okay, so today, if this is clear to you, then that winds up the discussion. So we are going to discuss applications today, okay, the applications of differential equations. Differential equations is everywhere. It's very important to study. So this section is pretty much a little bit of a marketing strategy, and also otherwise. Why is it important? Why is it a marketing strategy? Because we are going to sell it to you. Okay, the study of differential equations is very, very important because it appears in several different scenarios. Why is it otherwise? Because I mean, I'm a math guy. I'm not an engineer or anything, so I don't know anything. But based on the kind of questions that was asked to me in the previous semester, the differential equations appear in environmental engineering, circuits, and these are the two popular questions that I got. So I'm going to discuss some applications, and the applications are going to be dealing with, one is the circuit theory, the second one is the compartmental analysis, the third one is population dynamics, the fourth one is Newton's law of cooling, and the fifth one, hopefully if we have time, we will talk about the applications of differential equations to money, which is interest rate problems. Okay, so that's the plan for the day. Let's see how much we achieve it. Okay, this is a series circuit. So I mean, you must have, my physics is a little old, but you must have studied physics very recently, so you will know more than me. This is a series circuit. What do I mean by series circuit? There is only one way to go, one way for the current to pass in the circuit, right? Parallel circuit means there is more than one way for the current to pass through the circuit. Okay, so this is a series circuit. It's pretty much mentioned here. And V of t is the external voltage, and R is a resistor. R is a resistance in the circuit. Resistance is measured in ohms, and it's represented like this, I think. And the inventor of the resistor is called ohm, and that's why the units of measurement is ohms. L is the inductance. And I think the father of inductance must be Henry. So it's measured in Henry. Okay. Now in this series circuit, we have a resistor and a inductor. What is an inductor? Any coil is an inductor. At least that's the way I studied in physics. Okay. Don't dispute my physics much, because I do not have any depth in physics. It's very shallow. So so what we have here is a series circuit in which there is an external voltage, and there is a resistor, and there is an inductor, right? There is a Kirchhoff law. I mean, again, Kirchhoff's law. Because of my stay in different continents, it's said as Kirchhoff, whatever. So that's a law. The Kirchhoff is a person who said that the external voltage is pretty much distributed between the resistor and the inductor. So the total voltage is the sum of the resistance voltage drop across the resistor plus the voltage drop across the inductor. Okay. So voltage drop across the resistor is given by I times R. Actually, the voltage drop across the resistor is proportional to the current passing through it, and the constant of proportionality is the resistor. That's the way I studied it. So in this case, R is the resistance, I is the I of t is the current in the circuit at the time t. Current in the circuit at time t. Okay, so so I'm gonna write this as, okay, in this case R is 10, so I can write this as 10I, right? And the voltage drop across the inductor is VL, is going to be L di dt. Again, the voltage drop across the inductor is proportional to the rate of change of current in the circuit, and the constant of proportionality is the inductance, which is L. So in this case, L is 1/2, so 1/2 di dt. Okay? So using the Kirchhoff's law, the total, so I have 1/2 di dt plus, 10I is going to be 12 volts, right? It's 12 volts. Is that clear? Nothing complicated. Right? For a beginner like me, it's all nice and sweet. So now we know that because this is the first order differential equation, I mean, I'm a math guy, so this is the first order differential equation. The dependent variable is I, the independent variable is time. Is this linear or non-linear? Linear, right? Good. Is this autonomous or non-autonomous? Autonomous, because there is no time on the left hand side if I separate out the variables like that, right? So if I want to find the current in the circuit, I need to solve for I. So when I solve for I, what method would I use? What are my options and what method should I use? My options are?
Well, I was just saying, your options are graphical variable or integrating factors.
Okay, and what will I use?
Integrating factors?
Method of integrating factor. But however, can I use variable separable as well?
Yeah.
Yes, because it will fit into both. Okay, this is one problem where you can use any method and get away with it. Clear? So let's go about it now. Then you would multiply both sides by 2. So this will give you di dt plus 20I equals 24, where my initial condition I of 0 is going to be the initial current in the circuit is 0 amperes, right? And I'm assuming there is a person by name Ampere who discovered something to do with the current, and that's why they named it amperes. Am I right? Am I right? I don't know. You should tell. Okay, so let's go with the problem. I have di by dt plus 20I equals 24. Make the coefficient of I prime, step 1, make the coefficient of I prime equals 1. Make the coefficient of I prime or di dt equals 1, and it is already in that form, so step 1 is taken care of. Step 2 is identify what is my P of t and Q of t, and P of t is 20, and Q of t is going to be at 24. Do you agree with me on that? And step 3 is find the integrating factor. So integrating factor is e to the integral P of t dt. So that will give me e to the integral 20 dt. So that's going to be e to the 20t, right? Yes? Clear? So step 4 is I'm going to write d by dt of the dependent variable times the integrating factor is going to be integrating factor times the Q of t. So in this case, it's going to give me d by dt of dependent variable is I, e to the 20t is going to be Q is 24 times e to the 20t. So I want to find the current. So what do? I integrate both sides. When I integrate both sides, I get I times e to the 20t is going to be integral of 24 e to the 20t dt. Right? Yes? So I get I times e to the 20t is going to be 24 over 20. E to the 20t plus c, then I'm going to divide by e to the 20t on all sides. So I get I of t is going to be 24 over 20 times e to the 20t, plus c times e to the negative 20t. That is my current in the circuit at any given point of time t. So am I done with the problem? So what should I do? What should I do next? What is my next goal? Find the C. So step 5 is to find C. So how do I find C? I use the initial value, which tells me that T is 0, I is 0, right? Because the initial current in the circuit is 0. So when I substitute T is 0 and I is 0, so I get 0 is going to be 24 over 20 plus C times e to the 0. So this tells me that C is going to be negative 24 over 20. Right? Clear? Yes.
So is it always the case that the C is the same as whatever the first term is?
No. It depends on, I don't know. It depends on the problem. But for example, in this, it is not, you're looking at this one here?
No. I was referring to like the
Not always. Not always. No. It's just problem specific, and in this problem, it turned out to be that way. But we are going to do a few more problems now that you asked me. It occurred to me. As you go on to the next few problems, you will see that they will be different. Okay? Substituting that, you would get I is going to be 24 over 20 minus 24 over 20 times e to the negative 20t. Right? So if by simplifying, I can write this as 6 over 5 minus 6 over 5 times e to the negative 20t. So this is the problem. That's it. That's the current in the circuit at any given time t. So that finishes out the problem. Clear?
Can you go back for just?
Okay? Good? So that finishes out the problem. But this is, I want to go a little more and explain some more stuff, because that's the cooler part of the problem, for me at least. Okay, hopefully what I'm going to tell you now is just for fun. Okay, because that's what makes it differential equation special. If you just solve it, there's no fun. Okay, now as t goes to infinity, what happens? What happens to the current in the circuit? So that means you have a circuit where there is a resistor and inductor, you turn it on and you leave. So, and forever, and you don't ever come back. What happens to such a circuit? That's what we are discussing. So, where as t goes to infinity, I of t, what happens? It converges to 6 over 5. Very good. So, it converges to 6 over 5 because the second term goes to 0, right? So, what we say is the first term, 6 over 5, is a steady state term. That means the term that remains forever. Steady state term is I of t equals 6 over 5, because that's what remains forever. The transient term is the term that goes to 0. Is the term that goes to 0, and that is, negative 6 over 5 times e to the negative 20t. The transient term is transient. It goes to 0. You with me in that? That's the first thing that I want to tell you. And the second thing I want to tell you is the following. Okay, what was our differential equation? di by dt plus 20i equals 24. Do you agree with me on that? Now allow me to write this as di by dt equals 24 minus 20i. Do you agree with me on that? Yes? So now what is the first thing we learned in this course? It's the geometric method, right? Then variable separable, then method of integrating factor, right? So this is an autonomous first order autonomous differential equation, right? First order autonomous differential equation. So so we should be able to do all our analysis, correct? So let's do our analysis and see what happens. Step 1 is to find the critical point. So how do I find critical point? I said di dt equal to 0. So when I said di dt equal to 0, I get 24 minus 20i equals 0. So that's going to be, I is going to be 6 over 5. You see 6 over 5 returns, right? So the next thing is you want to find, okay, what is it, phase line? You want to draw the phase line. So when you want to draw the phase line, okay, this is 6/5. So if you pick I less than 6/5, so which value should I pick? What is it? 0? Okay, I equals 0, no current in the circuit, then you will get that I prime is going to be 24. So that's positive, so it's increasing. So you would put an arrow like that, right? And when I is bigger than 6/5, what value of I do you want to pick? 2. So then I is going to be 24 minus 20 times 2. So that's going to be negative. So the current in the circuit is decreasing. So you would draw a phase line like that. So your critical point I equals 6/5. What can you say about it? Is it unstable, semi-stable, asymptotically stable? Is asymptotically stable critical point? Asymptotically stable critical point. I hope you are enjoying it. See, you see, whatever you studied in the first section is still relevant. You know, it's not like done and dusted. You see, you could still go with that. So, so that's what you have, right? So the next thing is you want to draw the solution curves. Let's see what happens with that. So if I want to draw my solution curves, okay, so that is I equals 6/5. And I know that for the values of I bigger than 6/5, it was decreasing. For the values of I less than 6/5, my current is increasing. Do you agree with me on that? Now, my I prime was, 24 minus 20I. 24 minus 20I. So I double prime is going to be derivative of 24 is 0 minus 20I prime because of the chain rule. You with me on that? So now when my I is less than 6/5, the sign of I double prime is negative and I prime is positive here. So this is going to be negative. So this is increasing, but is it increasing in but concave down? And when I is bigger than 6/5, what is the sign of the second derivative? It is going to be negative, and first derivative is negative as well. So it's going to be plus. So this is decreasing and concave up. So when you graph it, it's going to be like this. So it tells you that you see that the rough sketch of the solution for the differential equation that is arising in the LRC circuit would look like that. You see, I did method of integrating factor and got my solution, and t goes to infinity. I could say my current in the circuit goes to 6/5. But let's say if let's say the universe stopped right after the geometric methods and we never found out what is the method of integrating factor or variable separable, you can still say, okay, as the t goes to infinity, the current in the circuit still goes to 6/5 because the 6/5 is an asymptotically stable critical point. Is that clear? I don't see the happiness in your faces. Okay, but that's really nice. Okay, that hopefully at some point of time it'll appeal to you, because whatever we learned using the analytical methods of the law of computation were exactly justified by the qualitative behavior that we studied in the very first section. That's what it is. Okay, now that's about the circuit. So the next kind of problems is we want to deal with the compartmental analysis problems. The popular one is the tank problem that you are seeing here. So the next few problems are going to be dealing with the tank, but it's really nice problem. Okay, a tank contains 200 liters of fluid. So you have a tank and it has a 200 liters of fluid. Okay, and there is 30 grams of salt that is dissolved in it. So initially there is 30 grams of salt. If there is a 30 grams of sugar in it, then it becomes a soda, right? Coke or Sprite or anything, 35 grams of salt, sugar actually. So a fluid containing 1 gram of salt per liter is then pumped into the tank at a rate of 4 liters per minute. So there is an incoming fluid. So that is the concentration is 1 gram per liter, and the speed is 4 liters per minute. Okay. So there is a fluid that is coming inside the tank carrying the salt concentration of 1 gram per liter and coming in at the speed of 4 liters per minute. The moment it comes in, it gets mixed up in some fashion. I mean, in some random fashion. We don't have a handle on that. And the well mixed solution is then pumped out at the same rate. Okay, then it is pumped out at the same rate, meaning it's going out at 4 liters per minute. Are you with me in that? Now, if the incoming speed is the same as outgoing speed, then the volume in the tank remains a constant, right? If the incoming speed is faster and the outgoing speed is slower, then the tank will overflow, right, at some point of time. If the incoming speed is slower but the outgoing speed is faster, then the tank will become empty at some point of time. Are you with me on that? Now, this is a tank problem. But this can be applied to anything. I mean, think of it like, I-75 or I-85. That's like a tank. There is always some number of cars on the interstate, right? There is an inbound traffic, then there are cars exiting the interstate as well. So if the incoming rate is faster and outgoing is slower, then there will be a traffic jam, right? If their incoming rate and outgoing rate is the same, then the traffic will be nice and smooth on the interstate, right? If the incoming is slower and outgoing is faster, then at some point of time, the interstate will be empty, which is a contradiction. That can never happen, right? Do you agree with me on that? That's one scenario that you can think of. The other scenario you can think of is the tank is your, let's say, the tank is your bank account, right? The incoming is your salary, outgoing is your expenses. Are you with me on that? I don't need to explain much after that, right? You can think of your home loan or a car loan or any other loan that you can think of. Incoming is the amount you're paying to pay off the loan. Outgoing is the way it's growing. Are you with me on that? So it's very even though we are going to call it as a tank problem, it's a very universal problem. Are you with me on that? Or if you go to Boston, it's like the problem is getting onto the subway, which you will never be able to between 3 and 5. Okay, that's the problem. You see, it's pretty much the same thing. So let's look at this. Now, we know that we are doing a tank problem, but it is very universally applicable. So with that new dawned understanding, let's go ahead and understand this problem some more. So what are we going to do? We are going to, the next one has a fancy picture, but this one doesn't, but that's okay. So the rate of change of dq dt, okay, q of t is the concentration of the salt in the tank at time t, right? I don't know what it is, so I'm going to call it as a variable. Okay, and dq dt is the rate of change of concentration of the salt in the tank. Okay, the concentration keeps changing, right? So if the incoming fluid has more salt, then it mixes and the solution becomes more salty. If the incoming fluid has no salt or a pure water, then what happens? It becomes diluted and the salt concentration decreases. So the salt concentration is changing with time. So that's why dq dt is the rate of change of concentration at any given time t. Is that clear? Now what we would see is that the dq dt depends on incoming concentration minus outgoing concentration. So it is rate in minus rate out. Now what is rate in? Rate in is incoming concentration times the incoming speed. Minus outgoing concentration times outgoing speed.
Instead of concentration, isn't it just supposed to be the amount of the salt? Because there's no, we're not considering volume.
Say that again, please.
Instead of concentration, isn't it just supposed to be the amount of salt? Because we're not considering it with respect to volume, just the amount of salt that puts into the point, not the concentration as in like
We are considering concentration, right? See, because the reason is, you say in this problem it said a fluid containing 1 gram of salt per liter. So it is not just the amount of salt, it's the salt per liter. So if, like, I mean, in my experiment, like if I'm letting it go for, if I'm letting in 2 liters, then it's like, I mean, 2 grams of salt. So it's an incoming concentration. And so this is when I say dq dt here, right? Now, then dq dt is q is the grams and t is the time. So I have grams per minute or grams per second or grams per hour on the left hand side. Do you agree with me on that? Yes? Oh, okay, so I write dq dt is going to be incoming concentration for me here was 1. So 1 gram per liter times the incoming speed is 4 liters per minute minus outgoing concentration. What is the outgoing concentration? It is some grams per liter. So, do you agree with me on that? So how many grams of salt? I don't know that, so I'm going to call it as a Q. But how much is present at that? The initial volume, which is 200, plus the incoming volume, which is going to be 40, minus the outgoing volume, which is 40. Do you agree with me on that? I will repeat. Outgoing concentration. Outgoing concentration is grams of salt per liter, some liters, right? How many grams of salt is present in the outgoing fluid? I don't know that, right? Because it got mixed up. I don't know how much is going to be there, so I'm going to call it as Q. But what is the fluid that is there, that is present in the tank at the time? It is 200 plus 40 minus 40, because it is the net volume that is present after it gets mixed up at any given time t. Yeah.
Is that Q the same Q?
It's the same Q.
Well, when we defined it earlier was the concentration, and now we're just using it as like total volume.
Q of t is not the concentration, it's just amount. Because that's just in grams. This is just in grams, or so that's the amount of salt, that's not concentration. Okay, times the outgoing speed, which is going to be 4 liters per minute.
What are you multiplying by 4?
What is it? Yes, Roman?
Oh, what are you multiplying by 4? Like, what?
Because that is the outgoing speed, right?
Oh, okay, you don't count that.
Yes. So this gives me dq dt is going to be 4 grams per minute minus 4q divided by 200 grams per minute. And with my initial value being q of 0 is going to be 30 grams of salt. Clear? So this is also grams per minute. So I mean, this is also in grams per minute. So the dimensions match up. Clear? So upon simplifying, I get dq dt is going to be 4 minus q over 50, and q of 0 is going to be 30. Okay? And after that, you can either use variable separable method or the method of integrating factor to find out the and solve for Q. Okay? Can I leave it like that? Is that okay with you? Because you have done more, you have seen enough problems using method of integrating factor, so is it okay to leave it like that? Would you finish it out? Or is there anyone who wants to see the whole work? You good? You want to see the whole work?
Sure.
Yes? Okay. So dq dt is going to be plus q over 50 equals 4 and my q of 0 equals 0, right? No, not 0. Q of 0 is 30, I think. That's what I have, right? So the integrating factor, no, the P of t here is 1 over 50. And Q of t is going to be 4. So integrating factor is e to the integral P of t dt. So that's going to be e to the integral 1 over 50 dt. So that's going to be e to the t over 50. Then we know that because it is a linear problem and I'm using method of integrating factor, I can write this as integrating factor times the dependent variable is going to be the right hand side, which is going to be e to the t over 50 times q, which is going to be a 4. So I integrate both sides. When I integrate both sides, I get q times e to the t over 50 is going to be 4 over 50 times e to the t over 50 plus some constant c. So my goal is to isolate the value of q. So I'm going to divide by e to the t over 50. Remember that exponential term is never 0. So you would be able to divide by the exponential term. So that gives you q is going to be 4 over 50, which is 2 over 25 plus c times e to the negative t over 50. Okay. So now my next goal is to find c. To find c, I use the initial value. When t is 0, my value of q is going to be 30. So obviously, I'm going to substitute those values. So I get 30 equals 2 over 25 plus c. Then that gives me c is going to be 30 minus 2 over 25. Is my work right so far?
No, it's 200 e to the t over 50.
Say that again.
It's 200 e to the t over 50. Instead of 4 over 50.
You're right. This should be 200, right? Thank you. So this is going to be 200 e to the t over 50 plus c. So this will give me 200 plus c times e to the negative t over 50. Then that gives me 30 equals 200 plus c. Then c is going to be negative 170. Then substituting c equals negative 170, I get 200 minus 170 times e to the t over 50. Okay? Are you all okay with that? Any questions? Okay.
Just a question. When you said divide by e or 50, why did you set it not equal to 0? What is that?
Because division by 0 is undefined, so I'm just making sure that my division is appropriate. See, when you say divide by, we only learn dividing by numbers, never by functions. I mean, very rarely. Whenever, like quotient rule, when you took the derivative of the quotient rule, you always made sure that the denominator is never 0. So that's the same logic. Okay? So to answer your question, you see the c is never the first term now. In the previous problem, we had a question, the c was always turning out to be 6 over 5. It's the first term. But in this case, the c turned out to be negative 170. It's not equal to 200. So that way the c value is different. Okay? Clear? Okay, now the next problem is very same problem, only there is a change in the scenario. You have 200 liters of fluid, 30 grams of salt. Incoming concentration is 1 gram of salt per liter. incoming speed is 4 liters per minute, and outgoing is 3 liters per minute. The outgoing speed is slower. That's the only change. The rest of the stuff remains the same. Do you see that? Is that clear? The scenario is exactly the same. The difference being the outgoing is very similar. The only difference being the outgoing speed is 3 liters per minute, not 4 liters per minute. So how would it work? I mean, you would go the same way. The dq dt is rate in minus rate out. Rate in is the incoming speed times the incoming concentration. Incoming speed is 1 liter per minute times incoming concentration. No. Incoming speed is 4 liters per minute. Incoming concentration is 1 gram per liter. So that's going to be 4 grams per minute. That's what is the incoming rate in, right? What is the rate out? Outgoing speed, which is given to us by 3 liters per minute. In outgoing speed would be Q divided by 200 is the initial value, plus the incoming volume is 4T, minus the outgoing volume is 3T, so the net volume is going to be positive T. So that's going to be 3Q divided by 200 plus T. Do you agree with me on that? So your differential equation would be, okay, dq dt would be equal to rate in minus rate out. So that is 4 minus 3q divided by 200 plus t with the initial value q of 0 equals 30. And because the outgoing speed is slower and the incoming speed is faster, you would expect that the tank will start overflowing at some point of time. Good? Any questions? Okay. Now, this again very similar problem. The fluid is 200 liters. The initial volume is 200 liters of fluid. The initial amount of salt in the tank is 30 grams. The initial incoming concentration is 1 gram of salt per liter, and the incoming speed is 4 liters per minute. But then this time the outgoing speed is 5 liters per minute. So the outgoing speed is faster than the incoming speed. So you would expect that the tank will become empty at some point of time during this experiment. Clear? Yes.
Because it's not continuous anymore, how would you solve it?
Say that again, please.
Because it's a non-continuous differential equation.
The previous problem, you mean?
Yeah.
Okay, the previous problem is I have dq dt equals 4 minus 3q divided by 200 plus t, where my initial value q of 0 is 30, right? Do you agree with me? You can use either variable separable or method of integrating factor. I will demonstrate how, and then I'll set it up but not really solve it. So one is if you write dq dt is going to be not t is going to be plus, plus 3q divided by 200 plus t equals 4. So in here the p of t is going to be 3 divided by 200 plus t, and your q of t is going to be a 4, right? So if you go with the integrating factor, you would say integral of p of t dt. So that's going to be e to the integral 3 divided by 200 plus t dt, right? So if you say 200 plus t is u, so then dt is going to be du. So this is going to be e to the integral of 3 over u du. So this is going to be e to the 3 natural log of absolute value of u. So that's going to be what? Absolute value of u cubed. So this is going to be 200 plus t cubed. Do you agree with me on that? So that's what is your integrating factor. So you would start by writing, okay, now d by dt of the integrating factor, which is 200 plus t cubed, times the dependent variable is q, equals the integrating factor, which is 200 plus t cubed, times the right hand side, which is going to be a 4. right? And you would start solving from there. Is that clear? Or you could use variable separable as well. How would you and go on? Is that okay if I stop here? Okay. Then I want to, now that you raise the question, I just want to address like how would it be if I go through variable separable. So dq dt is going to be whatever I have, right? 4 minus 3q divided by 200 plus t. So this will be dq dt is going to be, what is that? 800. So I cannot use variable separable on this. I thought I could use. I was wrong. So plus 4t minus 3q divided by 200 plus t. So I cannot use, variable separable on this. I was wrong. Clear? That's how you would proceed. Okay? Good question though. I was, in my head I was thinking, okay, I can pull it off, but I couldn't. Thank you for asking me that. Okay, so here is the problem. This problem, the scenario was exactly the same except that the outgoing speed is 5 liters per minute. So how would I go with that, right? So rate in minus rate out. So rate in is the incoming speed, which is going to be 4 liters per minute. The incoming concentration is 1 gram per liter, so that's going to be 4 grams per liter. So that is my rate in, right? Incoming concentration, right? Rate out is going to be, the speed is going to be 5 liters per minute, and outgoing concentration would be the same thing again. I don't know what it is, so I'm going to call it as Q, but the net volume is going to be 200 plus 4t minus 5t grams per liter. So that's going to be 5q divided by 200 minus t. Correct? So then I would write my differential equation as dq dt is going to be 4 minus 5q divided by 200 minus t, where my initial value is q of 0 is going to be 30. Clear? And I'm going to use the method of integrating factor to find q. Find the amount of salt at any given point of time t in the tank. Clear?
Can you go on the yeah, for the first one, wouldn't the units be grams per minute?
Yes. Thank you. The liters gets cancelled out, so I get grams per minute. Yes.
So basically, the fact or the technique that we learn how to use for linear differential, for at least a linear equation, those only work on that only works on autonomous equations.
No, you can.
Or you like the
See, if you are saying method of integrating factors and autonomous, that means there is no t in it, right? If there is no t in it, then you could use variable separable also on that. If there is a t, then you would end up using method of integrating factor.
so the method.
There is no t means what? Q of t is 0. If Q of t is 0, then you could use variable separable. You could use method of integrating factor, but method of integrating factor, the right side is 0, so there is no integral that you're really evaluating there. Clear? Okay. So, I mean, the question that you're asking is, if I have dy by dt plus p of t times y equals q of t, right? And if you're saying something is autonomous, This means I would write this as dy by dt equals q of t minus p of t times y. If you're saying something is autonomous, what are you meaning? You're meaning two scenarios. One scenario is q of t is 0, or in other words, q of t is a constant and p of t is a constant. You have to take away t. The only way you can take away t is by making them constant. But if you make them constant, you could end up using variable separable. That's what it is.
Alright, okay.
You see what I mean? If it is a constant, what would you write? You would write dy by, if it is a constant, you would write this as dy by dt equals some constant k1 minus k2y, right? And that would be just variable separable. But that's, it depends on the problem.
Can you go back?
Okay? The next one is, okay, the same scenario, 200 liters of fluid, 30 grams of salt is dissolved, pure water is pumped in, and 4 liters, it is coming in at the speed of 4 liters per minute, and you're pumping it out at 4 liters per minute. Is that clear? So, how would you model such a scenario? Rate in is going to be, incoming speed is 4 liters per minute, and incoming concentration is 0 grams per liter. The reason being, what is pumped in is a pure water, it has no salt in it, so the incoming concentration is 0, so which will give you 0 here, right? The outgoing speed is 4, is it 4 or 5? It's 5, so you're going to write this as 5 liters per minute. And outgoing concentration is again Q divided by 200 plus, 4T minus 5T. So that's going to be 5Q divided by 200 minus T. So if you have this, the differential equation for you would be dq dt is going to be 0 minus 5Q divided by, is it 5Q? Yes, 5Q divided by 200 minus T, where my initial concentration Q of 0 is going to be 30 grams. So you get dq dt is going to be negative 5Q divided by 200 minus T, and Q of 0 is going to be 30. So that's going to be, again, here you could use either variable separable or method of integrating factor. Clear? Everyone okay with that? Any questions? Okay. So that takes us to the next problem, next application, which is the population problem. Okay, the population of the yeast grows at a rate proportional to its size. So P of t is the population of the yeast at any time t. dP dt is the rate of change of population with respect to, it is the change in population with respect to time. So the rate of population is proportional to its initial size. So you can write this as, dP dt equals Kp, where your K is the constant of proportionality. K is the constant of proportionality, right? Do you agree with me on that? Okay. So now you can write it, okay, you want to find the population at a given time t, so you can separate out the variables dP over P is going to be K dt. You integrate both sides. When you integrate both sides, you get natural log of absolute value of P of t is going to be K times T plus C1. You want to isolate P, so raise it to the E. So you write that. This is a very computational process, right? So this will give you that P of t is going to be C times e to the kt, where your C is going to be e to the C1. Okay? I'm going to upload this notes along with the video, so you don't have to be busy writing whatever I write. Is this clear? So the population is P of, the population at any given time t is going to be C times e to the kt, correct? The initial population that is given to you is 4,000 cells. So, I mean, t equals 0, p equals 4,000, initial value is p of 0 equals 4,000. You must have seen this problem in calculus. I mean, so this is going to be 4,000 equals c times e to the k times 0. So, which tells you that c equals 4,000. So, this tells you that p of t equals 4,000 e to the kt. Agreed? You with me on that? Clear? The next is it doubles after 3 hours. So that means the population doubles after 3 hours. So when t equals 3, the population is going to be 8,000. So substitute those values. So you get 8,000 equals 4,000 times e to the 3k. So that gives you 2 equals e to the 3k. So obviously you apply natural log on both sides to find the value of k. So this is 3k. So k is going to be 1/3 natural log of 2, right? So what is the value of k? I evaluated in the previous class, but I don't remember the value. So let me look it up. It is 0.231. Okay. So this, when I substitute that into my equation, then I get the population at any given time is 4,000 e to the 0.231 t. Do you agree with me on that? That means the population of East is growing at a 23% rate. Are you with me on the, right? Yes.
Would we be also like on a test, what if we kept it as the 1/3 ln2 and then evaluated it so it became 2 to the t over 3? Would that be fine?
It's fine. Okay. Now this is very, Syria is experiencing 6% population growth. United States is experiencing 0.63% population growth. Just to give you a perspective, in Portugal is experiencing negative 0.12% population growth, and East cells are experiencing 23.1% population growth. Now that anyway you're here, I just wanted to give you some statistics. It'll be interesting, right? So can you really model the population growth of a country with this? Now, have you heard of this? I'm sure you must have seen this somewhere, compounding interest, right? Did you see? So if you look at it, it is like if, I invested $4,000 in a bank account and it is growing at 23.1% rate per annum, what would be my value after a certain number of years? I can argue that way. And then if you're looking at it as a stock price, it is S naught e to the mu t, where mu is the growth rate. So I'm saying, I invested $4,000 in a particular stock and the stock is growing at 23.1%. So what will be the value of my stock price at a given time? So how much money am I going to make? So it's just the same. For a math guy, it's just the same equation. For applied people, they use different terminology to describe it. Okay. So here the value of k is positive. That's why it is a growth rate. Okay. If the population was negative, if the value of k is negative, then the population would be declining. Is that clear? Which happened in the case of Portugal, at least as according to the Wikipedia. I don't know the exact thing. Okay. So P of t is going to be 4,000 e to the 0.231 t. So what happens after 7 hours? So P of 7 is going to be 4,000 times e to the 0.231 times 7. You can evaluate it like that. We will come back to the population models in a big way towards at some point of time in the semester. We will talk about it more, but until then, this is the way. Clear? Yes? All good? The next popular one is from physics. I mean, Newton's law of cooling. I mean, you all heard of it again. Nothing surprising. And the reason I picked up these problems is because your web work really gives it. So I just wanted to give you some familiarity before you get in there. Okay? Newton's law of cooling says that the uppercase T is the temperature of an object. Lowercase t is the time. T is some external temperature or anything like that. So the rate of change of temperature is proportional to the difference in temperature. So suppose, I mean, the body temperature is 98.4 degrees Fahrenheit, but if the external temperature is 32 degrees Fahrenheit, if you go outside, you experience certain kind of, there will be decrease in body temperature. But if your body temperature is 98.4 degrees Fahrenheit and the external temperature is 100 degrees Fahrenheit, when you go out, you will get warmed up. Are you with me on that? So that's a natural thing. So the rate of change of temperature in the body is proportional to the difference between it. I mean, you know it. It's not something that I need to tell you. You have experienced it and you know it, right? So that's what it is. So you can write, mathematically speaking, you can write this as K times T minus TE, where your K is a constant of proportionality. Okay, constant of proportionality. Clear? Now you see, in all the applications you can do that. What is the critical point? What is can I sketch the phase line? Is my critical points asymptotically stable, semi-stable, or unstable? You can do the same kind of analysis for every application. It's just that I did it only for once and I thought, okay, that's a quick demonstration, and you can do it like, when you're free, bored, just try it. It'll be really interesting. Now, what would you do? Of course, you will separate out the variables. Okay, in this problem, TE is given to be negative 10. So obviously, the differential equation will turn out to be K times T minus 10. Okay, so you would separate out the variables. So when you separate out the variables, what do? You do T dt T minus 10 is going to be K dt. Then you would integrate both sides. So when you integrate both sides, you get natural log of absolute value of T minus 10 is going to be KT plus C1. Yes.
It's C plus 10, is the temperature negative, right?
Thank you. I'm sorry. Okay. Then you would raise it to you want to isolate T, so you would raise it to the E on all sides. So that gives you plus C1, so that's going to be e to the KT times e to the C1, so that's going to be C times e to the KT. If you don't want to show these two steps, it's okay, you can just skip to the last one. So that gives you T plus 10 is going to be C times e to the KT. So your T, the temperature at any given time T is going to be C times e to the KT minus 10. Right? Now, of course, I want to find what is C, what is K. In this experiment, the initial temperature is 19 degrees. So T of 0 is 19. So that means when T is 0, when the time is 0, the temperature is 19 degrees. So obviously, I'm going to substitute that C times K times 0 minus 10. So this gives you C is going to be 29. So that tells me that, okay, my temperature at any given time T is 29 e to the KT minus 10. Okay. So 29 e to the KT minus 10. So now what the other information they tell me is that after 1 minute, the temperature is 6 degrees. So that means when T is 1, the T of 1 equals 6. So that means when the time is 1 minute, the temperature is 6 degrees. So I'm going to write 6 times 29 e to the K minus 10. So I got 16 equals 29 e to the K. So I get whatever I get. E to the K is going to be 6 over 29. So K is going to be natural log of 16 over 29. And that turned out to be a negative 0.594. Right? So that means the temperature is, the K value is negative, that means the temperature is declining. In the previous problem, K value was positive, so the population was increasing. In this problem, K value is negative, that tells you that the temperature is declining. So when you substitute back, I mean, you can now, you can substitute the natural log term or the decimal, whichever. So 29 e to the negative 0.594 at t minus 10. Right? Is that clear? You all good with that? Now, what happens? What will be the reading on the thermometer after 2 more minutes? So this is, okay, after 2 more minutes means T of 3. So that's going to be whatever that is, 29 times e to the negative 0.594 times 3 minus 10. You would evaluate it and get the value. Clear? Are you all good with that? That takes care of applications and the web work. So there is only one application that I need to demonstrate. The other application is the interest rate problem. Okay? I have just 4 more minutes. Okay, so I mean, let's say you put the money in your bank account and it is returning. What is the current interest rate? 5%? Approximately. Yes or no? You don't know? Don't care about the money? Very nice. Let's say it's some percent R, right? Okay, P is the principal. R is the interest rate. Or did you leave it to the Scheller School of Business? T is the time. Right? So, I mean, when the money grows, what is, I mean, the total money is going to be the principal plus the interest. So that's going to be, we're going to write P plus P times PRT, simple interest, right? You write it like that. Do you agree with me on that? Yes or no? So, I needed to write this on this slide. Okay, that's fine. So, so after 1 year, the money would be something like, okay, principal plus whatever the interest. So that means I'm going to write P times P of T times R times delta T is going to be just 1 year, right? 1 year has passed by, so that's the money. So if I want to measure like what is the amount after the 2 years, that is, then it is going to be the principal plus the interest. So that's going to be my principal is going to be P plus, PR plus the, I get P plus PR times just the R. Are you with me on that? This is my principal now. That is my PR times T is going to be just 1 year. So, right, it is just 1 year. Is that clear? Or if you want to go directly from here, it's going to be, you're going to write this as P plus PR times 2. Do you agree with me on that? Now, after 3 years, it's going to be P plus the initial principal plus the interest. So I will write this as PR times 3. Do you agree with me on that? Yes or no? Now let's say every year you are adding some amount of, like every month, let's say you want to add some amount of money, like $100. So it's going to be $1,200. $1,200 in it, $1,200. Like every year you're adding $1,200 to your account. So whatever is accumulating plus 1,200, right? Are you with me on that? So generally speaking, you would write this as, okay, in general terms, you would write this as P of T plus delta T is going to be the principal plus the interest PR delta T plus the additional amount that you're investing per year. Is that clear? So if you write it now, you can write this as P of T plus delta T minus P of t is going to be PR delta t plus K delta t. So this is going to be, now if you divide by delta t, so this, and as delta t goes to 0, you get dp dt equals Rp plus K. So this is the incoming or the growth in the account, and this is the incoming money. And this is outgoing if you're looking at it as a loan. And if K is positive, then the money is growing. If K is negative, then the principal is going to 0 with respect to time. Is that clear? Now we'll stop here and I will continue with the problem in the next class. Okay?